Good afternoon, ladies and gentlemen. I hope you can hear me clearly. Welcome to our March 2021 technical presentation from SAIMM. We're delighted to have a presentation from the Gold 1 team. The title of the presentation is Replacing the Function of Hard Rock Pillars with Concrete Support. And the geotechnical engineer there at Gold 1, Schalk Prinsloo, is going to undertake the presentation. Schalk's provided us with a very brief abstract. If I could just trouble you by reading it quickly. This is the content of the proposed presentation of what's happening now. Gold 1's Model East operations are in the process of replacing the function of their non-yield pillars with carefully designed concrete-based support. The concrete packs are designed to replace the function of hard rock pillars when the pillars are mined. Most of the hard rock pillars, especially in high-grade areas, have alleviated some of the mine's production challenges and gives the mine flexibility with sustaining its gold production. Furthermore, it lends the mine the opportunity to extract close to 100% of its available ore reserves. That's what we're going to be hearing about today. Very exciting stuff. I just wanted to say a few words about Schalk, if I may, and then hand over to him. Schalk Prinsloo is a geotechnical engineer. He received his Chamber of Mines rock mechanics certificate in 2016. He's undertaken quite a few postgrad courses at the University of Witwatersrand, the most recent in March 2021. Schalk started off his geotechnical career with the Open House Management Solutions team. He's subsequently worked at Two Rivers Platinum, Samancor Marula Shaft, and undertaken the work from 2017 to present at Gold 1 Model East operations. He's carved a career out, a name for himself in hard rock, shallow geotechnical design and planning. So we look forward to hearing Schalk's presentation today. So without further ado, Schalk, I'm going to hand over to you, and we look forward to your comments. Thank you, Schalk.
Thanks so much, Graham. Thank you so much, Graham.
Pleasure.
Okay. Thank you, Graham, and thank you all for taking the time to attend the online presentation on replacing the function of hard rock pillars with concrete support that I will be doing on behalf of Gold 1 Model East operations. In this presentation, we'll be going through the disclaimer, the location of the mine, the geotechnical environment, the mine plan, the pillar mining concept, and that will include the design approach to testing of the concrete samples, below deformation graphs of these tests, and the theory to practical comparison between the test and what the theory and what we practically saw, and estimating the concrete pillar strength, the implementation of these concrete packs underground with them replacing the function of the hard rock pillars, the challenges we had while implementing the value added to the mine, and then at the end I'll just do a few acknowledgements. At this point of the presentation, it's important to note that the presentation contains a patented mining method protected by OHM's innovations. The patent application number is 2019-05-483, and the priority date is 21 August 2018. The location of the mine is located in the town of Springs. It's located about 30 kilometers east of Johannesburg, and it forms part of the Central Rand Group ore body. the geotechnical environment is the mineable ore reserves, the buckshot barite leader reef, which we call the BPLZ, the Upper Kimberley 9A, which we call the UK9s. So the BPLZs account for about 80% of the production of the mine, and the UK9s about 20%. It is planned that the future of the mine is to be mining 80% of the UK9A reefs once further development down these ore body channels are opened up. So the mining layout is a conventional breast scattered mining layout with mechanized development, and most of the stopes are 1.2 meter high stopes, both for the BPLZs and the UK9s. We also employ a mechanized board and pillar section, which accounts for about 30% of the mine's production. Mining depth is on average 320 meters below surface, and that's for the BPLZs. The UK9s underlay the BPLZs and dip in the southeasterly direction at approximately 8 degrees at most. So the extraction ratio in the conventional section is 88%, and the board and pillar section is 72%. There's only minor seismic activity on the mine, and the dominant geological structures on the mine strikes in the northeast to southwest direction and not northwest to southeast direction. These geological structures doesn't have a major influence on mining layout and mining, the mining layout. So also in the hanging wall, there's problematic dolomites that's associated with water. So here's just a simple schematic of the BPLZs where most of our mining horizon takes place. And then there's some basals underneath the BPLZs, which in some part of the mine is payable. If these basals are payable, it's extracted secondary up to 3 meters high conventionally. And if it's more than 3 meters, then that's where the board and pillar sections are employed. And you can see just underlaying all of the BPLZs or the UK9A. It's slightly exaggerated the dip of the reef here. Like I said, it's approximately 8 degrees at most. And on top, we have a strong quartzite in most of the places in the hanging wall. We have a strong quartzite of about 300 MPAs, but there is places where the dolomites get into contact with the reef, and that is associated with water. So this is just a mine plan. So all the purple you can see here is the BPLZs that are mined. Just underneath the BPLZ, we have the UK9 section, which we currently export 20% of our production from. Here on the southern side of the mine, there's a board and pillar section, and the far eastern side of the mine is also a board and pillar section where the basal unit of the reef is more than 5 meters high. Development on the mine is done mechanized, mechanically with 5 by 5 meter tunnels, and these tunnels are done on reef and then 20 meters below them on off reef as well. And the reef tunnels are used for access to the stoping, and the off reef tunnels are used for access, traveling and cleaning and hauling operations. So you can see here the structures which I mentioned earlier. There's not a lot of structures, and these structures doesn't have a major influence on the mining layout or stability on the mine. So before we started the pillar mining project, we had historic fall of grounds, and these are indicated with these blue hatching on the plan. It's not clear now, but if we zoom into it, the plan gets hatched at blue. So these are about 50 meters by 70 meters the 1 year. The 1 year is about 50 meters by 85 meters, and this one is about 25 meters by 110 meters. And these falls of ground, all of them had water ingress into the mine once the falls of ground occurred. Sorry, just let me go back here for interest's sake. Is that the places where we started the pillar mining, we started here on the northern corner of the mine. So this was our trial phase in this block here because it was isolated from the mine, and once success was reached there, we branched out all the way down here, down the shaft and decline area up to this whole block here. So this whole block here is extracted now, and then there's a piece here in the northern side that's extracted, and then the board and pillar section on the far east side is also extracted, all the pillars. So this is just a zoomed in plan for normally what it looks like in the stoping. So you have your 5 by 5 meter development reef tunnels that's coming in. From there are muck bays blasted in. From the muck bays, there are dip gullies from these dip or center gullies that they stope from them using advanced strike gullies. They clean the panel into the advanced strike gullies into the center gully that gets mucked into the muck base, and from the muck base gets dipped into the off-reef excavation, which you can see here in black, and from the off-reef excavations gets hauled out to surface using the decline system. So normally the first thing you will have is these panels mining, the normal stoping width of 1.2 meter, and after the mining of these panels, we install the concrete packs in the stope where the stoping has taken place, and once these pack has cured, we mine the pillars that were left between the panels. The desired outcome was that the mine was initially designed for a life of mine of 10 years, and it was planned to downscale the mine's production from 2018. So we wanted to implement a mining solution that extends the life of mine and prevents retrenchment of personnel, and at the same time extract as close to 100% of the ore reserves as possible. And a mining method that we can also use for flexibility in the mix for an optimal grade. So in saying that we wanted to employ that, but still keep the integrity of the underground workings, meaning that we have to ensure the safety of all the workers underground whilst mining the pillars. We have to replace the support function of the hard rock pillars with concrete-based support, as the dolomites in the hanging wall is associated with water, and the ingress of water can flood the mine, which will obviously close down the mine, and then ensure and then prevent all large falls of ground that can cause injury to workers or damage to infrastructure. So the design approach is that we sit with a rock strength which the pillars are situated in approximately 180 MPa. And now we want to replace the function of that pillar with a concrete pack of approximately 16 MPa. So there is ways to get the concrete strength up to about 80 to 100 MPa, but that's not very economical, and to pump that high strength concrete over large distances, it's quite an hassle. So what we've done is we looked at the support capabilities of concrete pillars or a function of the width to height ratio and not the material strength. So the squat pillar effect in rock mechanics is well known, which when you increase the base of your pillar in relation to the height, that the strength of that pillar increases as well. So we wanted to test if that theory applies to concrete as well. So what we did is we've tested 100 meters by 100 millimeters by 100 millimeters concrete sample, the base size, and 100 millimeters high. That is just to determine the material strength of the concrete we used. And then we decreased the height by 10 millimeter increments from 100 millimeters down to 10 millimeters, so that we can test the various width to height ratios of the concrete samples to see what effect width to height ratio has on these samples. So these are just some of the concrete samples after the test, and you can see with the 1-to-1 ratio, you get your normal failure profile, which have two shear planes interacting with each other, and then failure taking place along those planes. And then it's noticeable that as the width decreases, you get more of a stable core in the pillar and less interaction of these two shear planes. And then as there's little interaction between these shear planes, there is no obvious failure of the pillar core. And as you can see from the width to height ratio of 4-to-1, that your core is actually still intact, and these failure planes are not visible anymore. And it's believed that those failure planes are still active, but they form a confining core to the pillars. So as you can see here, your 1-to-1 ratio, you have that obvious shear failure plane. Then as you decrease the height of the pillar, you can see more of a core forming, and then up to a 5-to-1 ratio, you can see that you have an intact core with only the perimeter of the sample taking the stress. So there's no failure beyond your perimeter of your sample. So these are just the low deformation curves that we got from those tests. So you can see a 1-to-1 ratio, which is the blue line here. The material strength was approximately 20 MPa. And then as you increase the width to height ratio of the pillar, so too does the strength of the pillar increase. So if I can just use the 5-to-1 ratio as an example, you can see that it's gradually building up stress, and up until a point where it exerts some form of strain softening or post-peak behavior, if you can call it that. After that, it exerts a strain hardening of the material with deformation. So we used this part of the curves on all of these low deformation curves, where the first sign of failure was observed as our strength of our concrete sample. So you can see a 20 MPa material strength gives you a sample strength with a width to height ratio of 5:1 of approximately 110 MPa. So it seems that the width to height ratio squat pillar effect theory was true for concrete and hard rock. So here we tried to duplicate the results when we used a weaker material strength in the form of a 13 MPa concrete. So you can see the 1:1 ratio is a 13 MPa concrete strength, and then we use 5:1 as an example again, we get up to a 72 MPa sample strength with an increase with to height ratio. So this compares nicely with what is theoretically believed to happen inside a squat pillar, which is, you can see a width to height ratio of a hard rock pillar of 5:1, which you can have this failure point and a little bit of post-peak strain softening, and then plastic behavior, and then strain hardening. And you can see the samples we tested, especially the 20 MPa samples, you have more or less the same behavior as you would have on a hard rock pillar. So when we looked at the graphs, we can see there was a clear trend in towards these failure points, which we identify as these points on the graphs with increased width ratio, and that could actually be presented mathematically, which we use a formula, actually just a modified Headley and Grant pillar strength formula to estimate the concrete sample or concrete pack strength. So we chose that formula because it's the most common for determining pillar strength, and it's also used on Gold 1 for designing its current hard rock pillars. It's a simple equation that eliminates unnecessary complications because it doesn't have a lot of variables in it. So pillar strength was calculated on the point where the first sign of strain softening behavior was observed, as it was the most constant point on all the graphs. The strain hardening behavior after the post-peak, we are not taking that into consideration as yet, as it's very difficult to predict and it's not constant in its behavior. So here we tested the formula against what we got in the press. So the calculated strength versus the tested strength, and you can see there's a very good correlation between what we tested and what we calculated, and there was a standard deviation of approximately 5 MPa across 63 tests with a scale of 200 MPa. So it's approximately a 2.5% error rate in what is calculated towards what is tested. So obviously the Headley and Grant pillar strength formula also takes the size effect into consideration. So the size effect is a volume to strength comparison, which just states that with the increase of volume of your sample, if you relate that volume directly to the strength of the sample, the strength decreases as a function of volume. This suggests that if a sample comprises of a lot of parts, there can be a lot of weakness in that sample, which can cause a failure in the sample or weakness planes where failure can start to initiate from. So I've tested some concrete samples for the size effect as well. So what we did is we tested a 50 millimeter cube, a 75 millimeter cube, and a 100 millimeter cube. We tested 6 of them, and then the results we plotted as a function of volume. And you can see there's a negative slope as the volume increase towards as the volume increase, the stress decreases. So this is just constant what Headley and Grant found with their pillar strength formula. So the tested size effect does not decrease dramatically compared to the calculated strength. However, research indicates that there is a cutoff point to the size effect where the size of a specimen does not further influence the strength of the specimen. The cutoff point is not taken into account in the formula, and thus the formula will decrease the strength of the pack without limit. with the current slope in strength, the formula decreased the strength of a 6x6 meter pack with a 5:1 width to height ratio from 110 MPAs to approximately 81 MPAs. So that's a total of 27%. So obviously your formula doesn't take into account that there's a cutoff from where your size effect has an effect on your sample. So we had to predict where the slope will end up to decrease the strength of the sample with the size being the actual practical size we will use underground. And that's the slope of the sample you can see here, of the calculated results you can see here in the graph. So after we were satisfied that the squat pillar effect is also applicable to concrete samples, we used a 5:1 ratio to design our concrete packs underground, and this is just purely for the post-peak strain hardening properties of the 5:1 ratio sample, that if the design is undercooked a bit, we still have a safety net in that. And the concrete packs were also designed to an industry standard factor of safety of 1.6. So whilst we were mining pillars, the observations on the ground showed that hanging wall to footwall closure increased. The pillars in the vicinity of the mined pillars showed stress fracturing, and what was interesting is that just the next pillar, so it's an 8 meter by 4 meter pillar that is mined. So the next 8 by 4 meter pillar starts to show failure, and the next one shows very little failure, and the rest after that shows almost no failure at all. And then as the pillar is being mined, you see surface fracturing on your concrete packs. And then when mining on a large scale started to be implemented, that we saw that off-reef excavation experienced some stress changes, and that is due that all your stresses are point loaded towards a central point, and if that point is located above an off-reef excavation, it is subjected to stress changes, and it shows on the off-reef excavations. Then seismicity in the area also increased. So as the closure that increased as the pillar was mined is that we installed closure stations directly next to all 20 meters from where a pillar is mined. And we saw that in the first 3 days of the pillar being mined, the closure rate was quite high at 0.35 millimeters per day. And during the next 2 months, the closure decreased to about 0.16 millimeters a day. And from the first 3 months to a year, we saw that the closure decreased further to 0.1 millimeter a day. And after a year, closure normalized to what we normally expect in the mining environment without the pillars being mined. It is also important to note that as these pillars are mined over a year, that the mining is further and further away from the closure station, so it doesn't have such an effect on the closure station. What it just shows is that when you design, we normally design our pillars, and the blue line you can see here is the expected behavior of a normal hard rock pillar underground. So we design them to a factor of safety of 1.6. So when you mine that pillar, the pillars in the vicinity try to take over the load that was subjected to that pillar, and then those pillars are stressed highly, and when they are stressed highly, they fail because they exceed their design load, because they have now taken over the load supposed to be carried by the initial design pillar. So that failure occurs, and when that failure occurs, it only occurs up to a point where enough movement is generated for a concrete pack to offer some support resistance in the form that it's replacing the pillar. So from this is where we see our closure increasing, and also the seismicity that we started to pick up was also because of this, that as your pillar fails here, it's audible underground and you can hear it, and then that is recorded as seismicity. So we actually installed a full-scale seismic network on the mine currently. So these are some pictures of the packs, what they look like before the mining. So we pumped them into 2 meter by 3 meter width and length bag, and it's about 0.5 meter rise per bag. So we stacked these bags and we built them next to each other to form normally a 6 by 6 meter pillar underground. And we just use these bags because they are easy to handle and to transport. And if you have a burst bag, your spillages it's not that much because you only lose the volume of one single layer of the bags and not the whole pack. These are just more installations before mining takes place. And then these are some of the photos of those same packs after a year of mining, and all the pillars in the area is mined out. So in this particular area, the mining span where the pillars were completely mined out is about 320 meters to 460 meters. So you can see that there is some fracturing on the packs on the sides, but you can see some stress fracturing here on the packs on the sides, and towards the middle as well, you can see that they're starting to form these little stress-induced fractures. This is the condition of a concrete sample that was subjected to 200 MPAs of load. So you can see the condition of this sample where it's heavily fractured right around the perimeter of the sample with these huge stress fractures in the middle of it. So these samples we actually classified, well, these samples are samples that we could have subjected to the most load that the press allowed. So this is the worst condition we have seen a sample in after a test. So if you can just compare the conditions of that sample to the condition of these packs underground, we can say that we are confident that our design is where it's supposed to be on a load deformation graph. So if you can just see, this is a tested load deformation curve that we used in the press, and then this is the calculated load deformation curve of the concrete pack with the width to height ratio of 5:1 after we applied the size effect and the Hetland pillar strength formula, and we calculate them through a factor of safety of 1.6. So those concrete packs underground are just subjected to a load of approximately 43 MPAs. So that actually correlates well with the condition of the packs. You can expect that this is approximately a third of what the pack is capable of doing before reaching its first peak strength before the strain softening and strain hardening properties of the curve. So the implementation that from the production side is that pillar mining started in late 2017 as a trial phase. After the trial phase, production was increased to approximately 3,000 square meters of pillar mining per month, which is sustained up until now. So by doing that, the concrete cubes pumped underground is about 243,000 cubes. The square meters of pillars that were mined in that period of time is 72,000. The pillar mining gold production is a 1.7 tons of gold that we mined from the pillars in approximately 2.5 years of full production, and the life of mine added was 7 years. So along the way, while mining pillars, there was a few challenges, and the first obvious challenge was sourcing of tailings, that we need a lot of sand to mix concrete with to generate more than 200,000 cubes. So the tailings we sourced, we found that the plant is actually quite sensitive to the quality of the tailings we put in the plant, in the sense that if the tailings are too fine, that it blocks the mixer and the ranges. It compacts together the fine tailings and blocks the mixer and the ranges, and that affects your production. And then we also found that carbon content in tailings negatively influenced the strength of the concrete because it has a negative effect on the bonding phase of your cement. We also found that sweeping control must be very good in order to place the concrete packs, because we use approximately 60% of our stoping floor space to build packs on. So if there's sweepings there, it's something that cannot be reclaimed at a later stage. And then when building the concrete packs, the build quality must be of a high standard to ensure a solid concrete pack. As the packs are being constructed by using 2 by 3 meter by 0.5 meter high bags, you need to stack these bags tightly against each other and on top of each other to form a solid 6 by 6 or whatever size you need for your mining environment structure. We also found that cement spillages in stoping panels was a problem, as the same thing as if your gullies and your panels are not properly cleaned, the cement solidifies in the panels and that sweepings is lost. We also found that in our board and pillar mining area, we constructed packs up to 11 meters high. So the average pack size was about 6 meters high, but there were 3 or 4 huge packs where we build them up to 11 meters high. So to construct a pack of that height, there's a lot of risk involved in employees falling from the pack and getting up and down the pack, and also transporting material up and down the pack, and also the sheer volume of material that goes into a structure like that. A learning curve for us also was the stitching quality of the weeping bags. So these bags, we want them to be tightly squeezed against the hanging wall. So we pump them under pressure to get a very good contact with the hanging wall, so that you have as close to an active support as you possibly can. So if these bags are taking these high loads and pressures, the stitching normally tends to tear, but that problem was resolved in the first few months, but it was at the time a very big headache. And then we found that block ranges also has a huge negative influence on your production, as if you have a power failure, or you have failure of your pumps that supply water to your mix, and anything that interrupts the process of mixing the concrete and pumping it underground. If the cement in the ranges, like I said, ranges, we pump cement over a distance of about 2.5 kilometers. So all the cement that's in that range, and if it can't get flushed out, it solidifies in the range, and you lose the whole column of that range, which also it takes time to replace, and you can't use that range. So it affects your production as well. The value added of the pillar mining project to Gold One is that currently Model East plans 2,800 square meters to 3,000 square meters on strike pillars. So Model East was always planned as being 18,000 square meter per month mine. And this is sustained by adding 3,000 square meters of pillar mining. So the pillar mining assists with about 70% of the plant production, only in the terms of square meters. So pillar mining aided with taking pressure off the conventional sloping section. So even though the pillar mining only accounts for 70% of the square meters, the gold content in the pillar is as high as the pillars are left in high grade areas. So that takes some pressure off the mining grade on the faces. So which we can, if we get the mix right, we can have a lower mining grade on the faces, which is just subsidized by pillar mining high grades. So being able to safely mine historical pillars that has added significant loss of gold production and therefore revenue, while still allowing the operation to sustain its historical employee numbers. So that's one of the major things that we accomplish, is that we are actually sustaining our employee numbers on the mine after our 10-year life of mine expected, which we expected to scale down about a third of our employees. So now we can keep on those employees and keeping the gold as where it was previously. So it is now possible to optimally extract the ore body and maximize the extraction ratio. So Gold One will be, I think, one of the first shallow conventional mines to extract close to 100% of its available ore body. This time, I just would like to acknowledge the Gold One More's operation for implementing the project. Like I said, this kind of project is the first of its kind. It's never been done in a shallow mine in South Africa. Tim Wright, they assisted with the research and development of the scale models test. Electro Either World, or the mixing and pumping, they mix and pump the concrete underground and also construct the concrete packs underground. And then Chryso, our concrete technologist, for aiding in the concrete design and the concrete mix design. Thank you, that's it from my side. So I'll now open the panel to questions.
Thank you, Schalk. Maybe you can put your video on so we can see your face. Fantastic. Thank you. I'm just going to open up the Q&As. I've got a few questions myself, but I'm not going to butt in. What I should say before we take the questions is that Schalk is he's writing an MSc up at the moment at the University of the Witwatersrand. I don't know if you want to say anything more about that, Schalk. Is it about this work, your master's?
Yeah, the thesis will be about this work.
And a gentle plea from SAIMM, I hope you'll think about our journal, because I think there's lots of interesting stuff here. So do consider us as a potential platform for a paper sometime in the near future. We would certainly look forward to that.
Yeah, that'd be wonderful. Thanks.
Let's just go to the questions. Let's have a look. I don't know if you can see the Q&As there as well, and we can work through them. And I've got some as well. Let's have a look at the first one. It says regarding the mining, is essentially being applied as a form of retreat mining. I guess it's making reference there to your pillar extraction sequencing.
Yeah, initially the trial phase was done in the northwestern corner of the mine, which is isolated. So we've done the trial phase there in a retreat manner, but there's such little influence on the stability of the underground workings from the pillar mining project that we now employ them wherever we see fit and we see practical now. So it's no longer being done on a retreat basis. It's now being done wherever we have ranges available and wherever mining crews can move to, because it's obviously difficult moving all your mining equipment like winches and hydro power and all that to specific areas. So because of the little effect the pillar mining has on the stability because of the concrete packs we install, we can now mine it in any which place we want.
Thank you. Bushy, I hope that answers your question. And now, Mark, a blast from the past. Mark Button. Mark's question is: what setting time did you allow before mining the adjacent pillars?
The concrete takes about 28 days normally to reach more than 90% of its strength, but we are pushed to 21 days after the concrete has been set to mine the pillars. And then with mining pillars adjacent to each other, that there's no time frame that we stipulate for them to mine them, that you can mine two of the pillars simultaneously if you need to, as long as the concrete is installed between the pillars and the concrete has cured.
Okay, then we've got anonymous attendee. Please describe the concrete pillar size carrying capacity from day 1 to 56, and if they have fly ash in the mix, and what is the cost per cubic meter, and at what MPa strength, how much cement OPC is in the mix per cubic meter. Now, I don't know if we're going into the depths of patency here, so I don't know what you can answer and what you can't answer. Schalk?
Yeah, the patent doesn't cover any mix design. So the concrete mix design is a straightforward 16 MPa concrete mix that we use fly ash and OPC, which is normal cement, and then tailings. And then we have a binder, which we add from Chrysler as well. The carrying capacity of this pillar sizes, that's difficult because we have different width to height ratios, but I can tell you the material strength from approximately, we test them at a 1 day, a 3 day, and then a 14 day, a 21 day, and a 28 day. So we only expect a 16 MPa concrete strength. So we expect at about 21 days to reach our 16 MPAs. That just gives us more flexibility on mining, because the quicker the concrete sets, the quicker we can mine, and the more square meters available, quicker to mine. So we aim to get about a 16 MPa in 21 days. So the 3 days are normally 3 MPa, the 7 days are normally 7 to 10 MPAs. And then from there we get our 16 at 21 days, and it gets up to about 18 to 21 MPa material strength. The quantities we use per mix, it's difficult to say, but I think per cubic meter is about 200 kilograms of concrete, the OPC, or I mean your cement, and I think 200 kilograms of fly ash, 400 kilograms of tailings, and the rest is water and a 5-liter binder added. But I'm not 100% certain of these figures.
Okay. And then if we just move on to George's question. So George is asking the question whether this technology, you envisage this technology being taken up into the wider gold industry. Obviously, the first place would be the own Gold One stable, other reefs, other projects. And do you envisage this technology being applied outside of Gold One going forward? Do you have any thoughts on that?
Yeah, we have a couple of guys who are interested in looking into it. We would like to test it also on platinum mines, gold mines, chrome mines. So because it's not a function of your mining layout or your mining environment, it's just a function of your width to height ratio and the method applied. It can be applied to any operation really. It's just the only question is if it's going to be economically viable. And so for now, the projects we have done some feasibilities on, it seems to be feasible on all mining commodities.
Then Johan's question is, how is the stitching issue solved? And if I may, I wanted to piggyback on top of that. I had a couple of questions about the weeping bags. My first question was, sorry, Johan, for butting in here. My first question was the bags, have they been, is that part of the patent, the bags, or is it just a locally sourced product that you've used? That's the first question. It's locally sourced. So is it effectively something that's off the shelf that you can have manufactured locally? We don't have to import it or anything like that. Yeah?
No, Timrite supplies the bags to us on Gold One, but I believe Timrite has a patent on the bag itself.
Yeah. And then sorry, Johan, I'm butting in here. The other question was on the bags. I just had a query. Are they fire resistant, the bags? Have they been tested at all for that, or these are just standard bags at the moment?
It's standard geotextile bags, and what we tested is they're not 100% fire resistant, but the smoke coming from the bag is not toxic, in the case that it will catch fire. It won't bring harm to any employees inhaling that smoke. Okay.
And then Johan's question was the stitching issue. How did the stitching issue get solved, or is it still an ongoing challenge?
No, it got solved because they folded the bags on the corners, not folded it double, but folded it back on itself. So you have 4 layers then, and then they used a heavier material on the stitching as well, where they, and I think the stitching pattern also changed on the bag, which increased the strength of the stitching to a point where we no longer have issues with it.
Okay, thank you. Then Anonymous, second question, how did you avoid fall to ground or radiation cracking? You in the presentation you gave us an overview of some fall to ground incidents, or can you just expand on that?
So I think that the major contributor to preventing fall of ground is that you cover a lot of area with your packs, more than you usually would with your normal pillars, because the normal pillar, you designed a 4 by 8 meter pillar carrying a 25 meter span, and now you have a 6 by 6 meter pillar carrying only a 9 meter by 6 meter span, and that's just a normal 1.2 meter stoping width. So you have a very strong, competent support, and you have a lot of these units that cover a lot of hanging wall area. So that assists in preventing large falls. And to this date, I must just mention that from when we started pillar mining up to now, we don't have any falls of grounds that is related to pillar mining. The falls of grounds I showed in the presentation, that was just before we mined pillars. And that's how we discovered that there's a lot of water associated with the dolomites that rushed into the mine if these panels fall to such a large extent.
Okay, thank you. Then Mark is asking a question about, have you tried to install or implement wire meshing between the cement bags? Have you looked at that, enhancing the strength of the pillars through wire meshing and bracing type ideas?
Yeah, in civil engineering, there's a lot of work being done on that, and it certainly does increase the strength of the bags, and it also lends towards stiffness, which is also a very good thing in a shallow mining environment. The problem with that is to get it practically underground and incorporate it in a high production, high volume environment. It just brings along with it its own issues. But it's something that we have to do some more study into, if it's something that is critical for a mine not to allow a lot of movement, or they don't have the area for us to install these with the height ratio of 5:1 or maybe a 4:1 pack. Then we have to go and look at alternatives to lend its strength from maybe something like mesh or old scraper wire or anything else that can maybe assist in that.
Okay. And then Lucas is asking a question about the calculation of the factor of safety of 1.6. I don't know if you've got your calculator there and you could take us through it. No. I don't know if you can comment on that. You see, Lucas,
yeah.
you see Lucas's question.
Yeah, I see it.
Yeah.
So it's normal, just a tributary area theory, like you calculate with the Hentley and Grant pillar strength formula. So we just modified the Hentley and Grant pillar strength formula that it's applicable to our concrete packs. So you use the tributary area theory to calculate the load per pack, and then the Hentley and Grant formula for the strength of the concrete pack. And we've also done some numerical modeling in Map3D to estimate how much load is being taken per pack.
Okay. Mark is asking about load cells between the bags, whether you implemented that in your test work.
Yes, we installed some load cells into the packs, but it also brought along a lot of issues because it normally takes about 6 months from installing the pack till you actually get readable results. And in that time period, we found that gauges have failed and equipment got damaged and all that. But we had a load cell which stayed, and it's still installed in one of our packs, which showed a reading of approximately 25 MPa before it failed. But what actually happens, the pack was installed on a ledge, so the ledge started to fail, so the load on the pack reduced, so we couldn't get an accurate reading on what the load is in the pack. But yeah, the most we had before the footwall started to fail was about 25 MPAs.
Okay, and Les is asking about the hi there, Les from Old Kinross days. It's great to see you or hear you in the contribution. Les is asking about the concrete pillars and how they differ from those used at the cook shaft experience. Have you got any comment on that?
I wasn't heavily involved in the design of the pillars or of the packs on the cook shafts. I know they used castle packs, which were timber-based packs as well, and also some sort of cement packs. But to my understanding, they were only supporting a area where there's tensile zone problems. The approach we took is that we wanted to replace the function of the pillar as its design function, which is to carry the overburdened weight up to surface as a normal hard rock pillar would do.
Okay, and then Pushy's asking about the 28-day period, and he's querying whether ventilation is an issue during that period. Now, please help me here, Schalk. Is that reference to dust, or is it reference to heat pickup from the cement packs? Is that do you think where the question's coming from?
I think it could be a couple of things, and I'm going to answer it and with all the possibilities I can think the question is directed to. That I think the first thing is that you have these huge structures which block some of your ventilation going towards your faces. So that might be a problem where you have you block your ventilation from reaching your faces, but the spacing between the concrete packs is such that the ventilation can freely go through the packs. It actually assists in the ventilation control on the faces, because now it's easier to close down and channel your ventilation through your shaft or your mine, as you have smaller open areas to close down to direct your ventilation. In reference to heat, that heat does have, a colder environment does have a negative effect on strength of your concrete. So we tested that our ambient temperature underground is about 18 to 23 MPa, which is optimal for concrete curing. And because it stays constant, we normally get better results underground as we do in the curing baths and testing the samples on surface.
Just while you're on the concrete strength, sorry for butting in, Pushy. You mentioned carbon content having an impact on the cube strength. And please, just for my education and maybe for some of the listeners, what is the carbon source that you're making reference to here? Would this be lubricants and diesel from the trackless fleet? Where is the carbon actually coming from? Where are you picking up the carbon problems in the concrete, or is that something that you're still investigating?
It was when we started using unclassified or unburned fly ash as tailings. So the carbon content is still in the unburned coal that was part of the fly ash before it became fly ash. And that's where the carbon started to influence the OPC in the mix, preventing it from forming its bonds. That was actually picked up by CRISO, the concrete technologists, and they are the experts on that. That's just what in layman's terms I can understand from that.
No, that makes sense. It wasn't clear to me where the carbon problem was coming from. So yeah, that makes a lot of sense. Just moving on for Lucas. Let's see if we can interpret Lucas's question. There we go. He's saying, I think he's talking about, he's saying, oh, he's jumping around a little bit. Do you think this is equally applicable to the igneous environment? So I would interpret that as the lead, which you said that you're looking at applying this to other opportunities outside of gold. I mean, bushveld and other. I don't know if you want to comment on that, you know?
Yeah, I think it's 100% applicable to any environment. As it is an engineered support system, it can be engineered to cater for any mining environment. And with our project now at Gold One, I think in the igneous environment, I know they are very sensitive to movement. And with our packs we use at Gold One, mining out a 420 meter span by 360 meter span, we only experience 43 millimeters of closure. So that's minute, and that, like I said, that we don't have a set system where we mine it from our implementation phase. We mine any pillar in the area that's the most convenient to mine. So I think if it's a problem, the hanging wall movement is a problem in your environment, there's a system that you can apply that limits hanging wall movement, or you can look at strengthening your concrete pillars, or you can maybe stiffen them up with what the previous question said, with like mesh or something like that. So I think it's definitely applicable to the igneous environment. We're 100% confident.
Okay, so you see Mark's question. He's asking about the application of this to deeper sequential grid pillars in the Carpenville area. So moving into deep, ultra deep gold mining, I guess the classic school of South African hard rock geotech. I mean, you're focusing very much, Schalk, in your career on the shallow applications, and we can talk about that. But the deep level gold miners are asking questions about the applicability of these techniques to the conventional, or to the layouts they've currently got. Have you got any views on that? Any comments on that?
Yeah, I think it will be similar to my previous answer, because it's an engineered product. You can engineer it to any environment. I mean,
yeah.
It just depends on what the application will be. But in the past, there's a lot of success that's been gained by installing concrete support in deeper mines in the form of reducing seismicity and increasing stability.
Okay, thank you. And then just going forward, anonymous again. Do you perform drill strength 100 mil cores to determine the extent of microscopic damage on the concrete pillars? I don't know. We're going into the realms of concrete strength testing here. I don't know if you want to guide us in there gently, Schalk.
Yes. What we did is that we got our own core driller. It's a Yilti drill with a 74 millimeter barrel, which we use to drill cores from the packs. And what we found is that you normally get this microfracturing, or we suspect is microfracturing, the first about 5 centimeters to 10 centimeters of the skin of the pack, because that part of the concrete normally breaks off when you retrieve the core. But that can also be because of when you pump the bag under pressure, that all your fines, which is normally your cement, gets pushed to the outer corners of the structure. And that might be because that they have a cold fused there as well. But we suspect that might be microfracturing. And we haven't drilled a pack that is extensively fractured yet, because there are only a few of them. It's only 3 or 4 of them. I had to go looking for packs where there's a lot of fractures on them, like I showed in the presentation. And these fractures are normally large enough that you can just stick your hand into them to see how deep they are, or just break some of the pieces off next to the crack to see how deep they are and the extent of that. But in the sense of determining microfracturing with the cores, we can say about 5 centimeters in the pack, we found that the core normally breaks off at that point.
Okay, Russell wants to contribute on this. Russ? Do we, Russ?
No, but no, not me.
Got Russell
No,
would like to answer the question live.
No, I'm just killing them as you're going through it. So I'm just trying to keep them current for you.
Okay, thank you.
Just trying to administer on your behalf. Apologies.
Thank you, Russ. Then just going down to Lucas's question here. Lucas is saying, let's read it. Pillar is stressed even before you cut it. What do you think happened with this load when you remove the pillar? It surely cannot be displaced to the neighbouring concrete pillar. I think you did talk briefly about this, didn't you, during the presentation? I don't know if you want to reiterate that.
Yeah, but what we saw is that when you mine the pillar, that the pillars in the direct vicinity of the pillar that you mine out, they start to show failure. So that you have a pillar that was mined out, an 8x4 meter pillar, and the next 8x4 meter pillars on either side of that pillar, where there's only a 2 meter holing separating these pillars from each other, those pillars start to show failure. And then next to those pillars, you see a little bit of stress fracturing, but not as much that you can say the pillar is starting to fail. But after that, there's no influence of stress. You can see that induced stress, if I can say that, from the mining the pillar. So what we see happen on the ground is that you mine your pillar, the pillars next to it start to show stress fracturing up until a point where they fail. And when they start to show failure, the concrete packs start to show fracturing as well. So we assume that the load from that pillar that was mined is transferred to the existing pillars, and from the existing pillars, when they can't handle the stress anymore, movement is generating for that failure to occur. And when that movement is generated, the pack normally offers the support resistance required to take over the function of the mined pillar.
Okay. Mark's come back with a second question. Let's just look at Mark's question. He's querying the, or is referring to the factor of safety 1.6, and he's asking, what is the maximum stress that the concrete pillars are subjected to? Question mark. So at 320 meters, which was the average depth you mentioned in the presentation, the vertical stress is about 9 MPa. So at 70% extraction, 30% concrete pillars, I can calculate about 30 MPa.
Yeah, that's about the ballpark. We don't have just a stoping height of 1.2 meters. We have secondary extractions where we extract up to 3 meters high, and then some places are 5 meters up to 11 meters high. So I'm just going to use the 1.2 meter stoping heights as an example. So for that factor of safety, using our own pillar strength formula, we calculate about 43 MPAs on the concrete pillars. But I must also mention that modeling shows, the numerical model shows about approximately 30 to 35 MPa stress on these pillars.
Okay. What we've got then is, Jan's just pitched in and said thank you. That's a compliment to you, Schalk. And Anonymous has come in, he's asking about pumping distances. So I think there was an earlier question about logistics, and I don't know if we quite captured that. If could you just say a couple of words about the logistics from surface to delivery?
Okay, so the batching plant on surface is about 700 meters from our shaft, and then the pipes, it's down the shaft 300 meters to the mining horizon, or 320 meters to the mining horizon. And from there, the maximum distance is about 1.2 kilometers. So in total about 2 kilometers, and it depends on how they route their ranges, because obviously where you're pumping, you're blasting as well. So your ranges you have to be clever where you put your ranges, not to damage them with blasting. So our maximum pumping distance is about 2.5 kilometers from the mixing tank on surface down to the last open end where they pump the packs.
Okay, thanks. Les is just saying hello. It was great to hear your voice again. Oh, to see your email, Les. Lucas again has come back to us. He's asking about sedimentary rocks. And he's asking, do you think the laminated nature of sedimentary rock is assisting you to load the cement pillars, where in igneous rock pillars tend to bridge and collapse when the bridge breaks? So Lucas is asking about the reaction of your support system to, I guess, homogeneous versus laminated type rock structures. Do you want to just say a few words about that, Schalk?
Well, that's something that we'll have to find out once we mine in the igneous environment. Obviously, these concepts are well defined and it's been tested for, across the mining industry. But if you understand your mechanism of your hanging wall, you can engineer your support or your mining method to counteract these problems which you foresee, and just have a support, engineered support to sustain whatever you bring towards it. So if bridging is your problem, but I think what a big advantage is for the packs is that you get a very good contact with the hanging wall, meaning so that if there is a failure and you cover such a large area of your mine, which you don't normally cover with your pillars, that you have you don't have as much room for failure to take place. So if bridging occurs and the collapse occur, that there is a lot of support that will offer support resistance for that bridge and carry the hanging wall. But that's just something that we need to investigate. And if the failure mechanisms, the hanging wall is well understood, we can design and engineer to ensure that we counteract these effects.
Okay. And Pushy's asking about the nature of the patency. So I guess you're on a thin line now. So he's asking the use of what is effectively being patented? The use of the concrete to replace the pillars, or just your concrete design? Surely not the pillar extraction itself. So I don't know. Can you make a comment about the scope of the patency?
Yeah, the concrete design is a normal 16 MPa concrete design. So that's not patented. I'm not sure even you can patent it. It's just the mining method in which you replace the function of a pillar underground with a support medium.
Okay. Okay. I hope that answers your question, Pushy. Then Anonymous, okay, what is the amount of cubes you can do per day? So it's productivity, and how do you get all the material underground to pump the packs? I think you've handled the second part of the question. Logistics, can you give us some indication of your productivity?
Yeah,
Schalk?
certainly. We use positive displacement pumps to pump the concrete from a mixing tank into pipe ranges underground, and one of these pumps normally delivers on a 7-hour shift 30 cubes of concrete. So whatever you need underground, you can just multiply whatever the amount of pumps you will need. So 30 MPAs per pump on a 7-hour shift is the average going rate. So we use an 8-stage plant and we get approximately 9,600 cubes per month out of it on a 2-shift cycle.
Okay, now Francois is asking a question about the application of the Headley and Grant type formula. So we just read it carefully. The assumption of using a Headley and Grant type formula to estimate the strength is an interesting choice. When looking at he's looking at the 1972 Canadian paper, a large number of crude assumptions were made to derive this formula. Would a linear formula perhaps not be better for which the strengthening effect for the strengthening effect of a large concrete block? So he's questioning the use of that particular formula and asking and looking at possibly some other approaches. I don't know if you've got any comments on that, Schalk.
I do. I think there were some crude assumptions made because in that formula there was only about 4 of the pillars that failed when they derived the formula. So from our formula, we had 63 concrete cube samples, which we all destructed, and we all have data on them, low deformation data on them on different points. So that's why, and the other reason why we use the Headley and Grant formula is that because we still use it now at Modern East for our hard rock pillar design. And the paper also includes a nice section in the paper where it deals with the size effect. So that was a major thing for us, is that you're testing a 100 millimeters by 100 millimeters sample in a press, but you're implementing up to some places a 15 meter by 25 meter concrete pack over 11 meters high. So obviously size effect will have a huge effect on what you use underground currently practically. So that was the reasoning why we used the Headley and Grant formula. And when we used the Headley and Grant formula, there was a 5 MPa standard deviation across the 63 test, and the scale was about 200 MPAs, which is the most loaded we got on a pack. So the formula predicted the failure of the concrete samples quite well in the press. So by manipulating the exponents on the formula, we got very satisfactory results from the Headley and Grant formula. A linear formula could perhaps work. We haven't looked into it yet, but it's something that we might look into.
I think that's the next paper that you and Francois are going to write together. Anonymous is asking about the cost per cube. I don't know if you're at liberty to share costs with us at this stage.
I have a ballpark for normal concrete pumping underground and constructing these packs, and it's about 850 meters per 50 rands per cubic meter, and that's just a ballpark, a quick and easy rough estimation of it. So that includes your material, the labor to pump it underground, and the labor to construct the concrete, the bags or the packs underground as well. And this is derived from when they use small packs, 1 meter by 1 meter packs, up to the packs that we use, 25 by 15 meter packs. So 850 rand per cube, it's a good ballpark for industry, right?
And just maybe a question from myself on one of the indirect benefits of this would be, you mentioned that there's a challenge to actually source suitable tailings material. Now, clearly, you're sourcing the fly ash type material from Eskom, and that's readily available in your particular locality. Is one of the benefits of this methodology you're putting together that there's potentially some environmental cleanup here? There's some environmental benefits to the surrounding area, and I think that's something which maybe needs to be stated going forward. Yeah. I don't know. Is that a reasonable comment to make?
100%. What Gold One is currently doing now is that we are looking into using our own tailings, because we're sourcing tailings now from an outside source. So we are looking to use our own tailings from our own tailings dam to be pumped back underground. So obviously you reduce the size of your tailings dam, and if your design allows it, you can deplete your tailings dam like to even levels before mining. So it's definitely a big environmental benefit to use the tailings. And if you can use your own tailings, you bring down your pumping cost of the concrete significantly as well. So it's a win-win.
Okay, fantastic. I think that's about it for now. I think I'm going to hand over. Well, I was hoping to hand over to Dani.
Yeah, he's fallen off. His internet fell over, Graham.
Russell, do you want to say a quick thank you on behalf of SAIMM?
I will do that with pleasure. Yeah, Dani sends his apologies. He got his internet fell over on him. So on behalf of the Joburg branch, Schalk and Gold One, thank you for a fascinating presentation. I must admit, to this poor metallurgist, a lot of it was over my head, but certainly interesting to see what you can do with the tailings that we produce. So yeah, good for that, and great to see the environmental liabilities of closure and that sort of thing being addressed in such a positive fashion. Thank you for that.
Thanks so much.
I wish you all the best for your masters. I'm sure there are a lot of students, hopefully, that have been sitting on this call eagerly awaiting the publishing of your thesis to cite and quote new technology. We would also like to offer you, or to send you, a small token of appreciation to say thank you for your trouble this evening and for putting together such a fascinating and professional presentation, which we'll arrange to have sent through to you in the near future. So, Schalk, thank you again, much appreciated. It just remains to say thank you to all the attendees and the SAIMM Secretariat for arrangements. But most of all, Schalk, thanks to you and to Gold One, and Graham, to you for arranging it. Thank you all.
Thanks so much for the platform. It was quite an interesting thing. Thanks, you.
Thank you, Schalk, and good luck with the Masters. We watch with bated breath And as we said earlier, we hope you consider SAIMM Journal as a platform for a paper in the future. But
Yeah,
please don't
definitely.
hesitate to contact us about that going forward.
Okay, great. I will do so. Thanks so much.
Cheers.
Okay,
Terrific.
bye-bye.
Thanks, everybody. Have a good evening further. Good night.
Good night.